Hi friends. Welcome to my channel. Please like the video and subscribe to my channel if you like the video. Slide 1. In this video we try to study about the topic, simple stress and strain, from the subject strength of materials. This subject is the continuation of subject, engineering mechanics, which we have already studied. Engineering mechanics deals with study of static and dynamic properties of a rigid body. Rigid body is a type of body which doesn't deform at any applied force. This type of bodies doesn't exist actually. Strength of materials deals with the study of behavior of flexible bodies. Flexible body is the body which deforms according to the magnitude and direction of applied force. The bodies which are practically available with us are of this type. Slide 2. Here we are going to see what are the standard units we use to solve the problems in this subject. The units of force or load or reaction are in newtons. The conversions are shown here. 1 kilonewton equals 1000 newtons, which is equals 10 to the power of 3 newtons. 1 meganewton equals 10 to the power of 6 newtons. 1 giganewton equals 10 to the power of 9 newtons. Length or breadth or width or depth or thickness are measured in millimeters, mm. The conversions are 1 meter equals 1000 millimeters, which is equals to 10 to the power of 3 millimeters. 1 centimeter equals 10 millimeters. Now, the units of area are square millimeters, square mm, and the conversions are as follows. 1 square meter equals 1000 square millimeters square. 1 square centimeter equals 10 square millimeters square. Slide 3. In this slide we are going to study about stress. This is simple stress, which is also called as normal stress, or direct stress. Stress is denoted with symbol sigma, as shown here, S, I, G, M, A. To understand about stress, first we will answer the following questions. Question number 1. Is it an internal property or an external property? Whenever you say that you are feeling stressed, what do you mean by that? Are you feeling stress inside the body or outside of the body? Obviously, it is an internal property, as we feel stress inside our body. Question number 2. Why do stress occur in the body? To answer this question, here, we are assuming a condition, where we are going to write an exam in a couple of days. Whenever we have an exam, we will study. While studying we take the workload, further feeling stressed. So, why do stress occur in the body? It's due to workload or just due to load. Next, question number 3. Whether you are fixed to take stress or not. To answer this, we are considering the same condition in which we have an exam in couple of days. Here, we are fixed to write the exam, so we are taking workload, therefore feeling stressed. What if we are not going to write the exam? There is no need to study for the exam. So, no workload. Therefore, no stress. So, for a body to be stressed, it should be fixed. From the above 3 answers, we can say that for a body to be stressed, first it should be fixed, second load should be applied, only then internally stress will be developed. Slide 4. By summarizing all the above 3 answers, we are defining stress as: it is an internal resistance offered by a restrained body due to loading. Restrained body means fixed body. Restrained is the technical term used for fixed. Mathematically, stress is also defined as the internal force acting per unit cross-sectional area. Sigma is equals to P divided by A. We know, units for force are in newtons, and for area it's square millimeters, denoted with mm square. Therefore, units of stress are newtons per square millimeters. Slide 5. In this slide we are going to study about strain. This is simple strain, which is also called as normal strain, or direct strain. Strain is denoted with symbol epsilon, as shown here. To define strain we are considering 2 cases here in which a bar of length L, which is fixed at one end, and is free at the other end. In case 1, On this body a force, P, is applied far away from the body. Here the body will try to elongate. When a force is trying to cause elongation in the body, then the force is called tensile force. Similarly, in case 2. On this body a force, P, is applied towards the body. Here the body will try to contract. When a force is trying to cause contraction in the body, then the force is called compressive force. Both elongation and contraction are collectively called deformation. So, when a load is applied on a body, there will be either elongation in the body or contraction in the body, depending upon the direction of the applied force. In both cases there is some change in length of bar. This change in length of bar is called deformation and is denoted with delta L. Now, strain is defined as the ratio of change in length to its original length. That is, epsilon is equal to delta L, divided by L. As the units of both change in length and original length are in millimeters, both will get cancelled and hence, there are no units for strain. Slide 6. Till now we have seen what is stress, its units, and what is strain, its units. Now we will see what is the relation between stress and strain. This relation is given by a mathematician named Hooke. So-called Hooke's law. Hooke's law states that within the elastic limit, stress is directly proportional to strain. Sigma is directly proportional to epsilon. Here, we are removing the proportionality sign and introducing a constant E. Therefore Hooke's equation becomes sigma is equals to E times epsilon, where constant E is called modulus of elasticity, or Young's modulus. Slide 7. In this slide we are going to study some properties of a material. Elasticity is the property of a material to regain its original shape even after removal of loading. Plasticity is the property of a material to not regain its original shape even after removal of loading. The zone below elastic limit is called elastic zone and the zone beyond this is called plastic zone. Plastic limit is the limit up to which body is safe, and beyond this limit body fails. Hooke's law is valid only in the elastic zone, that is below elastic limit. Ductility is the ability of a material to drag into wires. Malleability is the ability of a material to drag into sheets. The limit up to which body behaves as an elastic body is called elastic limit. Slide 8. In this slide we are going to see the different types of stresses and strains. First, in types of stresses we have simple stress or direct stress or normal stress, denoted with sigma. Shear stress denoted with tau. Bearing stress. Then, different types of strains are simple strain or direct strain or normal strain, denoted with epsilon. Shear strain denoted with phi. We will study the topic of shear stress and shear strain in upcoming chapters. Here we have to know only about the different types of stresses and strains. Slide 9. In this slide we are going to see about all the four elastic constants. 1. Young's modulus or modulus of elasticity, denoted with E. 2. Shear modulus or modulus of rigidity, denoted with C or G or N. Here I am considering G as the notation for shear modulus or modulus of rigidity. 3. Bulk modulus, denoted with K. 4. Poisson's ratio, denoted with mu. First, Young's modulus or modulus of elasticity, E, is defined as the ratio of direct stress to direct strain. E equals sigma by epsilon. Second, shear modulus or modulus of rigidity, G, is defined as the ratio of shear stress to shear strain. G equals tau, by phi. 3, bulk modulus, K, is defined as the ratio of direct stress to volumetric strain. K equals sigma by epsilon V. Epsilon V is the volumetric strain. Volumetric strain is defined as the sum of the strains in all the three perpendicular directions. That is in length, breadth, and depth directions. Therefore, volumetric strain, epsilon V is equals to epsilon L plus epsilon B plus epsilon D. Poisson's ratio, mu, is defined as the ratio of lateral strain to its longitudinal strain. Strain along the length direction is called longitudinal strain, and the strains along the other two directions that are breadth and depth are lateral strains. Mu equals epsilon b or epsilon d divided by epsilon l. Slide 10. In this slide we will see the relation between the elastic constants. We have four elastic constants, which are modulus of elasticity or Young's modulus, E, modulus of rigidity or shear modulus, G, bulk modulus, K, and Poisson's ratio, mu. The relation between all the four elastic constants is given by E is equals to 2G times 1 plus mu, which is also equals to 3K times 1 minus 2 mu. Slide 11. Now we are trying to derive equation for deformation in a bar. Before that we should know what the different types of bars are. There are two types of bars. Prismatic bar. Non-prismatic bar. If the cross-section of the bar is constant throughout its length, then it is called prismatic bar. If the cross-section of the bar is not constant throughout its length, then it is called non-prismatic bar. These two figures show the prismatic and non-prismatic bars. Slide 12. In this slide we are deriving an equation for deformation in a prismatic bar subjected to a load P. We know the equation of Hooke's law is, stress is equals to E times strain. Sigma is equals to E times epsilon. Now sigma is equals to load, P, divided by cross-sectional area, A. And strain is equals to change in length, delta L, divided by original length, L. Substituting these terms in the equation of Hooke's law, we get, P by A, is equals to E times, delta L, divided by, L. Further gives deformation, delta L is equals to P times L by A times E. Where, delta L equals change in length. P equals load applied. A equals area of cross-section, and E equals Young's modulus or modulus of elasticity. Slide 13. In this slide we are going to derive an equation for deformation in a bar due to its self-weight, W. We know that self-weight of a body acts at its center of gravity. The variation of self-weight on the bar is shown here. This has an ordinate of W kilonewtons at its fixed end and 0 kilonewtons at its free end. Therefore, average load acting on the bar is equals to W plus 0 divided by 2. Which gives average load, P, as W by 2. Substitution this P value in the deformation equation, delta L is equals to P times L divided by A times E. Now the equation for deformation in the bar due to self-weight becomes W times L divided by 2 times AE. Slide 14. In this slide we are deriving an equation for deformation in the bar due to both applied load, P, and its self-weight, W. Now, the total deformation in this bar will be equals to the sum of deformation due to applied load, P, and deformation due to its self-weight, W. Therefore, the formula for total deformation, delta L, is equals to delta L1 plus delta L2. Which gives, delta L is equals to P times L by AE plus W times L by 2AE. Slide 15. In this slide we are going to derive formula for deformation in the non-prismatic bar, which is a circular tapered bar. In circular prismatic bar, cross-sectional area is constant throughout its length. But here, in the case of non-prismatic bar, area is varying linearly. Therefore, cross-sectional area considered for this type of bar is equals to pi times d1 into d2 divided by 4. Now, by substituting this area in the general deformation equation where load is applied, the deformation formula becomes 4 times PL divided by pi times d1, d2 into E. Slide 16. In this slide, you can see the formula for non-prismatic rectangular bar with thickness T and breadth B1 at one end and B2 at other end. Slide 17. In this slide we are going to study the total deformation in a stepped bar. In this figure we have 3 bars with 3 different cross-sections connected together. Each bar have different cross-sectional area, length, and modulus of elasticity. Now, total deformation here will be equal to the sum of deformations in all bars. Delta L is equals to delta L1, plus delta L2, plus delta L3. Which gives us delta L is equals to P times L by AE of 1, plus P times L by AE of 2 and P times L by AE of 3. Slide 18. In this slide we are analyzing the stresses taken by each material in the composite bar, when subjected to an external load. In this figure we have two bars. Both the bars have different cross-sectional areas, A1 and A2. Made of different materials, that means different modulus of elasticities, E1 and E2. By analysis we have to find stress in each bar. 1 and 2. For that we need two equations. Equation 1 comes by assuming the bar on which the load applied is a rigid bar and its self-weight is neglected. By this assumption we can say that, total load applied on the composite bar is equals to the sum of load carried by both bars separately. Which gives total load applied, P, is equals to P1 plus P2. Rigid bar is defined as the bar with no deformation, whatever may be the load applied. And the second equation comes by assuming deformation in both bars is constant. That is, delta L1 is equals to delta L2. From the above two equation, we can find the required unknowns. Slide 19. In this slide, stress-strain curve for mild steel is shown. All the important points are plotted on the graph. Point A shows the proportionality limit. Point B shows the elastic limit, and zone OB comes under elastic zone. Beyond elastic zone material enters into the plastic zone. Point B is the upper yield point. Point C is the lower yield point. Point D gives the ultimate stress for the tested sample. And, point E gives failure stress. Mild steel gives a definite yield point when tested. Stress corresponding to the lower yield point is taken as its yield stress. Slide 20. All the materials doesn't show definite yield point. So for these types of materials, which doesn't show definite yield point, we make use of the concept of proof stress. Proof stress for these types of materials is calculated by drawing a parallel line to the initial portion of stress-strain curve, corresponding to 0.2% strain. That is at 0.002 strain on x-axis. This parallel line will cut stress-strain curve at a point, and the stress corresponding to this point is taken as yield stress for further analysis. Slide 21. Ultimate stress is the maximum value of stress that a material can resist. After ultimate stress is reached, material starts losing its strength and offers less resistance and eventually breaks or fails. Yield stress is the stress at a yield point or, at the yield strength. Safe working stress is known as the maximum allowable stress that a material will be subjected to, when it is in service. This stress is always lower than the yield stress and the ultimate tensile stress. The ratio of working stress to the yield stress or ultimate stress is known as the factor of safety. Slide 22. In this slide we are going to see about strain energy. Strain energy is denoted with symbol capital U. Whenever a body is loaded and the load is removed, some part of the energy is stored within the body. This energy is called strain energy. This strain energy depends on the magnitude of load applied on the body. There are some different terms which are used to define strain energy precisely, such as resilience, proof resilience, and modulus of resilience. Resilience is the amount of strain energy stored in a body corresponding to a particular load within elastic limit. This value depends on the load applied. So this value in a material is not constant. Proof resilience is the maximum strain energy stored in the body at its elastic limit. For any given material there will be only one load corresponding to its elastic limit. Therefore, proof resilience is constant for a given material. Now, modulus of resilience is the maximum strain energy stored in the body at its elastic limit, per unit volume. Or it can be defined as the proof resilience per unit volume. Strain energy stored in a material is calculated by finding the area under load versus deformation curve of the tested material. Slide 23. In this slide we are deriving a formula for strain energy stored in a body due to gradually applied load. Here, the figure shows the stress-strain curve of a material under gradual loading. We know, as the load increases, deformation in the bar also increases. If the load applied on the body is 0, then the deformation also will be equal to 0. Now, to find strain energy, we are considering area under this load versus deformation curve. As the area is in the form of a triangle, area of triangle is given by half times base into height. By substituting the values we get, strain energy U as, half times delta L into P. We know, delta L is equals to P times L by AE. Substituting this value in the strain energy equation, we get strain energy stored in a body is equals to P square L by 2 times AE. Multiplying and dividing the above equation by area, A, we get strain energy equation as sigma square times volume by 2 times E. Slide 24. In this slide we are deriving a formula for strain energy stored in a body due to sudden load. The figure shows the stress-strain curve of a material under sudden loading. Here, load is applied as suddenly as a whole. So we even see deformation suddenly without taking time. Now, to find strain energy, we are considering area under this load versus deformation curve. As the area is in the form of a rectangle, area of rectangle is given as length times breadth. By substituting the area value, we get strain energy U as, delta L times P. Again we know, delta L is equals to P times L by AE. Substituting this value in the strain energy equation, we get strain energy stored in a body is equals to P square L by AE. Multiplying and dividing the above equation by area, A, we get strain energy equation as sigma square times volume by E. Slide 25. In this slide we are deriving an expression for strain energy due to impact loading. Impact loading is the type of loading in which load is applied on a body for a fraction of time. That means load is applied and removed only for small time. The expression for strain energy in this case is same as in the case of gradually applied load. But stress in this case is calculated by the expression shown here. Slide 26. In this slide we will study regarding temperature, stress and strain. Whenever there is change in the temperature of a body, there will be either elongation or contraction in the body. As we know that, if there is increase in the temperature of the body, it will cause elongation in the body. Similarly, if there is decrease in the temperature of the body, there will be contraction in the body. But in a fixed body, the material will try to deform due to change in temperature, but as it is fixed at both ends it can't deform. So, stress and strain will be developed in the body, called temperature stress and temperature strain. To understand this, first we should understand what is coefficient of thermal expansion. Coefficient of thermal expansion is denoted with alpha, and it is defined as the change in unit length of a bar due to unit change in temperature. That means we are considering unit length and measuring its deformation due to unit change in temperature. This deformation value is taken as coefficient of thermal expansion. Now change in unit length of bar is given by delta LT is equals to L times alpha T, where L is the length of the bar and T is the change in the temperature. Now, we know, temperature strain is defined as the change in length due to temperature by its original length, which gives temperature strain, epsilon T is equals to alpha times T. Then, by Hooke's law, temperature stress is given by temperature strain times modulus of elasticity. That is, sigma T is equals to E times alpha T. This is the end of this chapter. Please like the video and subscribe to my channel if you like the video.